Hi, we'll get started. I'm not expecting a lot of people today just because it's almost finals time. But today will be the last in-person review session, and then next week I'll have a review session at the same time. It'll just be on Zoom. So look out for a link and whatever there. And then I'll do that for the final will be a final review session, like a final exam review session next week, and then I'll do an extra one either Saturday or Sunday. I'm just going to coordinate with Dr. Altimos. She'll take one day, I'll take the other. Mine will probably be Sunday, and then hers will be Saturday. And then final Monday, the 6th at 8 a.m. So you should have plenty of review sessions for this, and then the mock exam should be out by Friday. So plenty of time to work on that. Alrighty, I think that's it. And then just quiz 6 on Monday. So just make sure you're ready for that and everything as well. Alrighty, so are there any questions for me? That's not content. Okay, any questions content-wise that we want to go over today?
Like, do you know much about like the lab exam at all?
I don't. I work with lecture, not lab, so I don't know too much about it. But if you know what's on it, or you know like topics that you should know, we can review that for sure.
Don't focus on like the labs themselves. That's where I messed up. I focused like on the labs and like the content of the actual lab, and the exam is more like questions. Like it reminded me more of exam 1 and exam 2, like actual concept questions and like problem solving questions. A lot of like enthalpy and rate laws and stuff like that.
Any other questions? That's yours is tomorrow. I remember because I taught lab my first year that I was here, and I remember my students kind of have it a little rougher time than expected.
Review with the lab. Like
Yeah.
An example. You don't really know what to expect.
Yep. And there you do so much, it's all tied into the lecture, but it's like sometimes hard to bridge the gap. I get that. Alrighty, anything from that you want to review, or just general stuff? Yeah, do we want to start final review, or do we want to do a little bit of what we did in lecture today kind of thing? Are you feeling okay on? Yeah, okay, so just want to do like a couple little general review stuff? Sure.
Could we like beginning of the semester kind of like rate laws, like buffer, just like enthalpy, like just cover like maybe the general stuff?
Yeah, absolutely. Let me look back at the notes of what we started with because it's been a while. Yeah, so what we talked about towards the beginning of the semester, we'll do like kinetics and stuff first. So we talked about rate laws. So what determines the rate law? What part of the reaction, or what part of the steps determines the rate law? I might be asking this. So, well, first, right, what is a rate law? This tells us how fast a reaction is going. Oops, going. And it has the general, right? General skeleton of the rate of the reaction, or just the rate, is equal to K. This one is little k. Little k times the concentration of a reactant to the power m. So what is little k? What do we call that? This is a rate constant. A is a concentration, and this is always going to be a reactant. And what do we call M? What is determined with M? What is that exponent? Mm-hmm. Yep, so this is going to be your order. So your order is for that specific reactant. So whatever that reactant is raised to, that is going to be the order. We mostly talk about 0, first, and second order. But you can have an overall order of 3, 4, 5, depending on how many reactants are in your rate law. Okay. Kind of ring a bell what we've done. Okay. So looking at the rate, so then and the rate constant and everything like this, your rate constant, your units will vary. As in the concentration unit is what's going to change. And then it always needs to have a concentration component and a time component. So most often we see things in molarity and seconds, but you can have, right, hours, minutes for time and stuff like that. You can have different units of concentration, but molarity and seconds are usually your big ones. Okay. Alrighty. When we look at rate laws, right, your slow step is going to be your rate determining step. So if you're given a mechanism that shows this here, and this is your slow, your fast, and your fast. What would be the rate determining step for this mechanism? The first step, right? Step 1, step 1 is going to be, this is the rate determining. Determining step. Alrighty, so what would the rate law be for that rate determining step? What would be that right-hand side of the equation? Yep. Right, we'll always have little k at the front, your rate constant times A to the M times the concentration of B to the N. Do we know what the values of M and N are in this case? Why is it just one? Good, right, so when we break it up into a stepwise mechanism for an overall reaction, then we can use the coefficients that's in front of our reactants or reactants in order to determine what the power is or what the order for that reaction is. So this will look like rate is equal to K times A to the B. Okay, so what's the order on A and B? Yep, first order for both of them. What's the overall order of this reaction? 2. Yep. So we have A and B, our first order. So overall, second order. Okay, we got second order because we just added the orders of A and B together. So if B was second order, then it'd be an overall of third order. Okay, if we were to add up, right, if I gave you overall up here in this, what is this? A plus 2B plus F plus G. Plus G. I think that's right. All right, if I gave you the overall reaction of 2B plus F goes to D plus G, right? We can see that if we were to write the rate law for this, we can't use the coefficients in front of B and F because one, F is not a part of our rate law, right? It doesn't contribute, it's a fast step. And B is not second order, it's first order. So you have to break it up into the mechanism in order to write the rate laws for a reaction. What do we call C and what do we call E in our mechanism? Not spectators. What do? Did they get produced or consumed first? Are they produced and then consumed or consumed and then produced? Produced and then consumed. So what do we call something that is produced and then consumed right afterwards? And if you don't know what C and E are, what about A? What do we call A in our reaction? Perfect. Which can you tell which one is which? Perfect. Right. So A is going to be our catalyst. And C and E are going to be our intermediates. Okay, so a way to recognize this, right? A catalyst is always going to be consumed first. It'll appear in your first step and then produced later on, so at your last step, while an intermediate will be produced first and then consumed. So you see it produced in step 1 with C and then used in the next reaction in step 2 in order to produce D and E. Okay, so those are going to be intermediates there. Catalysts can appear in overall rate laws, and then intermediates cannot appear in overall rate laws. So if you see one, then you have to do some finagling in order to get rid of them in your overall rate law. All righty. Any questions on rate laws? Okay, and then just to like spark your memory, Remember, we have some of the experiments where you have like trial and it's 1, 2, 3. You have A, you have B, and you have rate. Right, you have some things where it starts off. Right, you can have stuff like this. And in these situations, you're looking for a trial in which your reactant is changing while your other one is staying the same. And then looking how that change in concentration affects the change in your rate. Do that correctly. That's easier. Right, so if we looked at, if we wanted to find the order for A, what trials would we look at? 1 and 2. So what's happening for A as we go from point 1 to point 2? Yep, this is doubling. And what are we doing to the rate? Also doubling, so this is times 2. So what's the order for A? Yep, so this would be first order. And then what about B? What trials are we going to look at there? One and 3. Yep. For 1 and 3, right, we're keeping A the same from point 1 and point 1, and then B is going from point 1 to point 3. So what is happening with B? What do we do when we go from point 1 to point 3? Perfect, that's going to be times 3. And what happens to our rate from 3 to 9? Also times 3. So what's our order for B? This is also first order. All right, so it matches the rate law from above. Any questions on rate laws? Any other questions on kinetics? Does this bring back memories from stuff we did at the beginning of the chapter of the year?
Concentration. The rate is like times 4.
Yes, yep. So, right, if we're looking at 0 order, this is times anything. And you have times 1, right? So your reactant is here. And your rate is here, right? So that'll be times anything and times 1. Right, you can multiply it by 1,000,000. Your rate is still going to be the same. For first order, that can be times 2. It'll be times 2. Right, so rate increases. Same as reactant. And for second order, if you have times 2, it'll be times 4. So rate increases power of 2 compared to reactive. And that's really all you need to be able to recognize. You don't need to do time or third order or anything like that. Okay. And then this plays into your straight line plots. So for 0 order, all of these are going to be versus time on the x-axis. What is our y-axis for a 0th order reaction producing a straight line plot? It is just the concentration, yep. It'll be a negative slope. And it'll be concentration versus time. What about first order? What is the axes on first order? Perfect. So this is going to be ln of your concentration over time, or versus time, excuse me. And what kind of straight line do we have? Is it a negative or positive slope? It is a negative slope. And what about second order? This is going to be 1 over the concentration. And what kind of line do we have here? Positive or negative? Positive. Perfect. So looking at our straight line plot, right, you can get a equation from this. So slope, right, y equals mx plus b. M here is going to have some sort of k rate constant component here. So m for first order is negative k. M for first order is also, or m for 0th order is negative k. M for first order is also minus k. M for second order is just k. So when you're looking for the rate constant based off of a straight line plot, if you have the slope, then you have k. K is never negative. So for your negative slopes, you're taking the positive answer of the slope. Right, k rate constant is never negative. Any other questions or any other comments about rate laws? I think that was pretty much all of chapter 20. Couple things that you might be able to ask from this as well is just half-life. All of these will be given to you on your formula sheet, so you just need to recognize which one is which. So you have concentration of A is equal to negative KT plus the concentration of A naught for 0th order. That's your integrated rate law. You have your natural log or ln of AT is equal to negative KT plus ln of A naught for first order. And then 1 over A is equal to KT plus 1 over A naught for your second order. Okay, and then the big one to recognize for half-life is T1/2 is equal to 0.693, or the ln of 2, whatever one, divided by K, and that's for first order. The half-lives for 0 and second order will also be given to you. I think everything goes 0 with first, second, 0 with first, second on your formula sheet. So just make sure you recognize, at least just memorize one, and then you can get the other two. Alrighty, questions there? Is there any practice you want to do with this, or just feel good reviewing? Good, okay. Then a couple people walked in late. We felt good about the stuff in class right now, so we just did a general review, but if you have questions about class and stuff right now, just feel free to answer or ask your questions. Or if there's anything specific you want to review, I'm happy to do that as well. Okay, any questions there? Good. Any specific questions you want to see? Buffers? Yeah. All right, so when we look at buffers, what are the components of a buffer that we need to see, or what makes up a buffer? We can have a weak acid and its weak conjugate base. Anything else? Kind of a trick question, right? Or the reverse. We can have a weak base and its weak conjugate acid. Okay. So as an example, right, we can have HF and F minus. We have a weak acid of HF. Its conjugate base is -1 hydrogen. So that's going to be F minus. Or for your weak base, we can have NH3 and NH4 plus. So your weak base is ammonia, and it's forming ammonium, NH4 plus. Right, its conjugate acid is always going to be +1 hydrogen. Okay. What is the big equation we use with buffers? We have the Henderson-Hasselbalch. I forget how to spell his last name. HH. And what is the Henderson-Hasselbalch equation? Perfect, right? We have our base over our acid. It doesn't matter if it's the conjugate base or just a weak base, right? You're always going to want to have base over acid. So I can even write this as. And some base over some acid. Alrighty, so when we have a buffer, we usually talk about titrations. And when we have a titration, we're going to do a weak acid with a strong base. So your weak acid is the thing that is in your beaker with a pH probe. And then your strong base is your titrant, or the thing that's being added to your weak acid. So this is pH and this is volume. So when we have a weak acid, strong base titration, right? An example of this might be HF and sodium hydroxide. Where is that going to start off? Where does a typical pH start off for an acid? Towards the bottom, right? Somewhere around 1, 2, somewhere around there. And when we initially add base, what is that going to do to our pH? Is that going to increase it dramatically or increase it like shallow? Shallow, right? It starts off pretty shallow and we don't see a big increase in pH. When do we see a big increase in pH? What is that point that we reach? Right, so we have to reach the equivalence point. And is the equivalence point for a weak acid, strong base going to be in the acidic or basic region? It'll be in the basic region, right? Your equivalence point for a titration will be in the stronger of the two components that you have, right? If you have a strong acid, it'll be in the acidic region for your equivalence point. If it's a strong base, it'll be in the basic region. If you have both of them, then that's when it's always going to be 7, right? It'll be neutral because neither one of them like wins this strength battle. But if you do have a weak and a strong, then whatever the strong thing is where it's going to end up. So at that point, we see a large spike in pH and then it levels out again. Okay. So your pH is going to be here, right? Your equivalence point. This is 7. It'll be, above 7. So for this one, this is your equivalence point. And this will be in the basic region. Okay. What do we call this point here, or this portion here, before we see that strong increase in pH? This is going to be your buffer region. And this is when we can use the Henderson-Hasselbalch. What do you have excess of in the buffer region? Do you have excess of your strong acid or do you have excess of your acid or your base in this region? You have excess acid, yep. And right, that makes sense because we're still in the acidic pH. So that acid is what's contributing to the lower pH of our titration here. So in this case, we have excess acid that's contributing to our pH. What about at the equivalence point? What's in excess there? Neither, right? At the equivalence point, what is happening? Yes, yep. So at the equivalence point, your moles of acid equal your moles of base. So you have no equivalence, or so you have no excess of an acid or a base in this region. What about after the equivalence point? What is in excess now? The base would be in excess, right? So after we have base in excess. So this one, you just use your normal ice table or normal strong acid or strong base breakdown for that portion of your titration. Okay, any questions on strong acid, or sorry, and weak acid, strong base titration? And then just remember that this is for this specific scenario. If we had a strong acid and a weak base, then this whole thing would just be flip-flopped and start in the basic region. Your equivalence point would be acidic, and then it would level out to a very acidic pH after the equivalence point. Do we want to practice one of these, or do we feel comfortable with those? Just reviewing. Absolutely. All right. Okay, so this question says you have 30 mils of 0.3 molar NH3. What is the pH of this solution after 10 mils of 0.1 molar HCl has been added? Do you guys want to try this, or do you want to walk through it together? Walk through it? Yeah, absolutely. Alrighty, so once we have our initial question, what do we think we need to start off by doing? Let's not jump to that one yet. Let's see what's going on first, right? So we have 30 milliliters of 0.3 molar NH3. What is NH3? It's a weak base, yep. And we have 10 milliliters of 0.1 molar HCl that's been added to the solution. What is HCl? This is a strong acid. Okay, so we have a weak base, strong acid scenario here. So now the question should be, okay, where am I, right? In my titration, am I at the equivalence point? Am I before or am I after? How do we determine where we are? What do we have to look at? We have to look at the number of moles of both our base and our acid that's in solution. How do we get to moles from concentration and molarity? I'm sorry, from concentration and volume. We can multiply them, yep. So for our NH3, we have 0.03 liters times 0.3 molar. So we have 0.009 moles of NH3. And then for HCl, we have 0.01 liters and 0.1 molar. So you have 0.001 moles of HCl. Which one is in excess? The base is in excess, right? So our limiting reagent here is going to be our HCl. So what happens to that HCl? It gets all used up, right? It gets all used up and it's going to react with what? It'll react with the base. Yep. So if we look at this, right, it's like saying NH3 and HCl form NH4 plus and Cl minus. Right, but those are going to react together. We have 0.009 and we have 0.001. All of your HCl will get used up. So you're left with 0.008 moles of NH3. What did those 0.1 moles of HCl turn into? Or what did those 0.1 moles that we used up, what does that turn into? It turns into product. Which product? Which product that we care about? The NH4 plus. Yep, so this will have 0.001 moles of NH4 plus, right? Because everything is 1 to 1 to 1. So we use up the HCl, it turns into NH4 plus and Cl minus. So we're left with 0.008 moles of NH3 and 0.001 moles of NH4 plus. Right, so why does this matter? This matters because now this thing here can turn into a buffer, right? This turns into a buffer. So in our buffer, we can write our usual KB expression. But what's different now? Do we have what do we use in terms of filling in an ice table? Do we use molarity or do we use moles? We use molarity, yep. So what are we plugging in for our initial concentrations? Can we use 0.008 and 0.001 directly? No, what do we have to change? We have to divide it by the total volume. What is our total volume? Yep, it should be 40 milliliters. We had, right, 30 milliliters of NH3, and we have 10 milliliters of HCl. So we have total of 40 milliliters. So we'll take, I'm gonna use this. Right, 0.008, divide this by 0.04, and this is 0.001 divided by 0.04. We have 0.2 molar and 0.025 molar. And now what can we use that in? And now we can use that in our Henderson-Hasselbalch, right? We have these concentrations of NH3 and NH4 plus. So now we're going to look at the pH of our solution. So now is the time that we're going to change our Kb into Ka. And how do we solve for Ka if we're given Kb? Through Kw, yep. So in our Henderson-Hasselbalch equation, it's pH is equal to pKa plus the log of base over acid. So can't plug in Kb into our Ka. If we plugged in Kb, then it would give us the POH. So you can solve it that way, right? If we did POH is equal to pKb plus the log, it's now flipped to acid over base. So you can do it that way, but then you have to do the step to switch it back to pH. Or you can switch your Kb to Ka, and then you can just plug it in directly to this equation. Mhm. Yep.
Okay.
Yep, specifically for Henderson-Hasselbalch, we give you the pKa one. So I think Ka is like 5.55, 56 times 10 to the negative 10th. Yep. Do we have everything that we need in order to solve this question now? Yes, we do. So now pH is equal to negative log of the Ka you just solved for. And then we have 0.2 over 0.025. Get a pH of 10.2. Does a pH of 10.2 make sense? I would say it does. The pKa of 5.56 times 10 to the negative 10, right? If you just did that portion of it, you have a pH of 9.3. So at a pH of 9.3, that's when your acid and that's when your conjugate acid and your base are equal to each other. However, in this case, we have a lot more base than we do acid. So since we have an excess of our weak base, we should be pulled more towards that basic side of our pH scale. So we should be above the pKa of our buffer in this case. we should be more basic. It is more basic, so that's a good check to see if you're on the right track for pH. Right, if when that turning point flips and we then have more conjugate acid than we do base, then we should be closer towards that 7-ish range for the pH there. Okay, does that help with the titration question? Probably the hardest ones is when you're before the equivalence point. I think there's just more math than when you are afterwards. So that's a good one. Okay. Any other questions? Anything else from a titration that you want to see, or does that help? Correct. Yes. Yep. So this one, we were before the equivalence point. Yep. So that's why we have to do the excess and everything there. This is because your weak part is in excess. Yep. Right, and we see that when we solve for our limiting reagent, we see that we have excess weak component here. Anything else on titrations? Let's see, what else is on? Okay, so then I guess, are there any questions for studying for the final in general? Yeah. I would look at all of your past quizzes and then all of your past exams. Even if you got 100 on everything so far, I would go back and I would do all of those questions again, and I would really sit there and explain to yourself why that answer is correct and like what concepts from that you are using, kind of thing. Like annotate all of the questions that you've done so far. Everything has or at least like all the exams have a answer key towards them now. So print them out, try them again, like cover up whatever it is. And then explain yourself. You can write it there, anything that you want right now, or like download it to your iPad. I would do that, and then I would do all of the questions backwards in a sense, right? You're always are finding an answer. So try and plug that answer into your question and see if you can come with one of the answer choices or one of the constants they give you in your question. Right, a lot of ways to test you is to ask it in one direction, but then on your exam, ask it in the reversed. So if you're practicing the reverse with questions you've already been asked, you know that it's the correct answer, so you should be able to get back to one of the numbers that they give you in the question beforehand. And then honestly, what I did for studying for chemistry when I was an undergrad is that my friends would sit in a room and we would look at our notes and we would just start asking each other questions of like either silly little things like what does it mean to be spontaneous? What is the sign of delta S when it's a spontaneous reaction? Stuff like that, where you just have to recall information, or we came up with our own questions, right? So looking at a titration question like this, right? I gave you this one, come up with your own. Well, maybe you say, okay, maybe instead of adding 10 milliliters, now I've added 50. What does that change to this question, and how does that impact the question there? You have a question to base off of it, now make it your own kind of situation thing. The more you just expose yourself to the questions, the less scary it is to come to a question that you haven't seen before because you've been making yourself up for the past week or so. So that would be my suggestion there. Kind of give yourself 5 or 10 questions to look at, to make up, to try, or give yourself like an hour to study and do your own practice problems there. But I would think the best is quizzes and exams. And then if you get tired of those, try and find similar questions in ALEX. If you think the ALEX questions are easy, make them harder, right? Based off of what you've just studied from your exams and your quizzes, see how you can take an ALEX question and just elevate it yourself a little bit more too. And that's always something that you can bring to me or Dr. Altimos and say, like, could they ask this from, is this a good question to ask that intensifies the question here or something like that? Yep. Does that help?
Yes.
Okay. Thanks. Any other questions for the final? I don't think so. I don't know if partial credit gets added to final just because it's the last exam. Yeah. I don't remember if she's done that in the past for her other exams. I don't think she has, so I would plan on it not. Yep. Thank you. Good luck. Any other questions for me? Are you feeling scared? Do we feel okay about it? Like a little just intimidated, right? Probably. It is a final, right? It is like kind of scary, but like she said in class, like probably 40% is going to be this new material.
It's just like you feel it's like less math or less like crazy math, but
Yep.
this stuff.
Yep.
It's more like easy. Oh, like this will always be this way.
Yes. Yep. So if you're, confident at least 40% of the exam, that's pretty good. And then all the other stuff you have seen before. So hopefully you can kind of recall some information. And then like she said today, right, we will be building off of a lot of concepts. We'll put some of them together. So I always think that a final is a very good time to like utilize your exam, right? We're probably going to ask you a strong acid question or a weak acid question. Like use that information in that question to help you with a different weak base kind of thing that we have. I remember looking at a question on my exam in chemistry and like flipping to an earlier question, being like, oh, okay, so if this is true, then that means that this thing has to be false, right? And then I was able to do a true false question kind of situation. So they are tools, they are roadmaps. So if you can use that to the best of your ability, that'll help you along the way as well.
You know, she makes like finals questions like similar to like the questions we've seen before in the other exams. Is it going to be very similar, just kind of reworded, or is it like going to be like completely new?
It'll be pretty similar. It will definitely be questions you haven't seen before. It's not like going to be like, oh, I remember this was question 12 on exam 1, right? It'll definitely be a new question, but it'll be the same concepts and it'll be the same types of questions. And I would say the difficulty is probably a little bit easier for the final, just so that it's a little bit more straightforward for the answer that we want you to get. It's also 40 questions in 2 hours, where you used to have 16 questions in an hour, 50 minutes. So it's like we're asking you more questions in less time. So we can't ask you the same difficulty of questions because you just will run out of time. Yeah.
Do you think the textbook for anything, or
I kind of use the textbook, but I kind of use that as like a last resort situation. More of like, okay, I've gone through all of my quizzes, I've gone through all of my exams. If I'm having difficulty with something on one of the quizzes or exams, I go back to the textbook and do some of the practice problems at the end of the textbook just for that topic, right? If you're like really struggling with, I don't know, delta S, right? Then you read the entropy section of the textbook, do their end of chapter problems, because that's specifically for all those entropy things. Yeah, does that help?
yes?
Great. And I'm gonna, once she puts out the mock exam, I'll put out a few questions of my own, based off of what I see on the mock exam as well, so that you have just a couple additional practice problems to work through.
Thank you.
Yeah, thank you all so much. If you need anything in the meantime, I'm around, so. And then next week's review session will be at this time, but on Zoom, because it's a reading day. You don't have to come to class or come to campus.